Yeah, so I'm Ioanna, and today I'm going to talk to you about our work on transparency dictionaries with succinct proofs of correct operation. And this is joint work with Abiram Kothapali, Brian Parno, and Srinath Sethi. So let's start with explaining what a transparency dictionary is. So a transparency dictionary is an untrusted service that maintains a mapping from labels to values. Users can query the dictionary to retrieve the values associated with labels and update the entries in the dictionary. And as you, Alfred, said before, they are very important for several applications, and they are the foundation for several security critical applications, such as public key infrastructure and end-to-end encryption. In the context of end-to-end encryption, the dictionary maintains a mapping from user IDs to the user's public keys, and it is responsible for distributing these keys to the users so that they can communicate securely with each other. And when the service is working correctly, it indeed enables secure communication. So if Alice wants to receive encrypted messages, all they need to do is generate a key pair and then register their public key with a dictionary. And then if Bob wants to send a message to Alice, he queries the dictionary for Alice's public key and then uses it to encrypt messages that only Alice can decrypt because she's the only one that has the corresponding secret key. Now, Alice and Bob cannot be sure that no one is eavesdropping because the dictionary is untrusted, and it's possible that it is controlled by an untrusted third party. If the dictionary is controlled by a malicious actor, then when Bob queried for Alice's key, they could return back a public key for which they own the matching secret key. And then this malicious actor could do a man-in-the-middle attack and decrypt all of the messages that Bob sends using their matching secret key, and then encrypt them again and send them to Alice. So because Alice and Bob do not trust the dictionary, they cannot be sure that no one is eavesdropping unless they have some assurance that the service is operating correctly. And ideally, this assurance will come from the dictionary, from the transparency dictionary itself. So whenever the dictionary executes some operation, it should produce a proof that attests that this operation was executed correctly. But what does it mean for the service to execute correctly? Or what should these proofs attest? So first, each lookup should return the correct value that is associated with the label in the dictionary. Second, the dictionary should not be able to erase any labels, and the set of labels in the dictionary should grow monotonically. Third, all updates to already existing labels should be done according to an application-specific policy. For instance, in the case of end-to-end encryption, we might require that whenever an operation is done to a user's set of keys, these operations should be authorized by the user, by, for instance, requiring that the operation should be signed by one of the keys that already is in the dictionary. So in order for all of these proofs to be useful in practice, we additionally want them to have some security and efficiency properties. So as for security properties, we would like these proofs to be publicly verifiable, meaning that anyone in the system should be able to independently check these proofs and get back a strong security guarantee that actually the service is executing correctly. Second, we want proving and verifying to rely on to require no trusted setup, nor rely on any trapdoors. Now, as for efficiency, we want verifying these proofs to be fast, meaning that the verification should be less expensive, both asymptotically and concretely, than re-executing the operations of the service. This implies that the proofs should be succinct, meaning that both proof size and verification time should be sublinear in the size of the computation that the service is doing. And last, the overheads of generating these proofs should be modest, and generating these proofs at the service should be affordable. Now, most of the prior work does not meet all of these properties. And as a matter of fact, a large body of work fails to meet the first three properties. Here I'm showing you some of the related work, but we discuss this related work in more detail in our paper. So as you see, most of these systems either don't provide public verifiability, or they require a trusted setup, or verification is not fast. And among all of these systems, there is a class of systems that does have these three properties, but unfortunately requires imposes very high proving overheads at the surface. And these are the works that combine cryptographic accumulators with succinct non-interactive arguments of knowledge. We call these snarks. So to give you a bit of context, so a snark is a tool that allows an untrusted service to prove that it has executed something correctly. And it's basically a certificate, a very short and easy to check certificate. And as for a cryptographic accumulator, this is a tool that allows the dictionary to commit to its state and then efficiently produce a membership proof relative to the commitment that an element is in the state. So our dictionary, Verdict, belongs in this last category of systems. So it is using cryptographic accumulators and zero-knowledge snarks and it offers all of these properties, public verifiability, untrusted setup, and efficient verifiability, while imposing modest proving overheads at the service. So let me tell you how dictionary works. So Verdict represents a state using a cryptographic accumulator and works in epochs. At the beginning of each epoch, the service commits to its state by publishing a digest to a public timeline. This public timeline can be a public ledger, such as a blockchain. And it also produces an update proof that I'm going to come to in a bit. So during the epoch, the dictionary receives updates from the users that want to register themselves or update their keys. And it buffers all of these updates. And at the beginning of the next epoch, it applies all of these updates to the dictionary, to its state, and then it commits to its state, producing a new digest, along with a new update proof. And this update proof is a snark proof that attests that the new state, the state that corresponds to the new digest, came from the previous state by only applying legal updates. No labels were erased, and all of the operations that were done to already existing labels were legal. Users are supposed to look at the public timeline and download all of the proofs and all of the digests and verify these proofs. And then when Bob now wants to read Alice's key, they do a lookup query to the dictionary, and they get back the reply along with a lookup proof. And this is a membership proof that shows that the answer is consistent with the latest published digest. Now, if Bob verifies all of the proofs in the timeline and the lookup proof, then they know that this is indeed Alice's key. In order to make this dictionary, to make this whole system practical, we have created a new snark and a new cryptographic accumulator. And these are both contributions that are of independent interest, and I'm going to talk to you about them briefly. So first, we designed a new zero-knowledge snark that meets Verdict's requirements, which we call Phalanx. Phalanx produces amortized constant-size proofs with constant verification times. So in the context of Verdict, that means that each of the users needs to download a constant amount of data at each epoch, and the work that each of the users needs to do per epoch is also constant. And users are also required to download and verify a logarithmic sized proof periodically, and this cost is amortized over many epochs. We designed Phalanx to leverage the SIMD patterns at Verdict's workloads, and we believe that Phalanx could be a good candidate snark for epoch-based systems in general. In the context of Verdict, generating proofs with Phalanx is more than 10 times faster than with Spartan, the system which has the prior fastest zero-knowledge snark prover. So also, Phalanx does not require a trusted setup, and its security relies on the symmetric external Diffie-Hellman assumption. And in the paper, we also have another system, another version of Phalanx that has different efficiency trade-offs, and its security relies on the discrete log assumption. Now, as for our cryptographic accumulator, this is a snark-friendly cryptographic accumulator that the dictionary uses to maintain its state. And what snark-friendly means is that all of the operations on this accumulator can be efficiently encoded in the circuit that our snark uses. And the key to this efficient representation is that this accumulator has efficient membership and non-membership proofs. Specifically, our accumulator is a variant of textbook Merkle trees. These support both snark-friendly membership proofs, but they provide membership proofs, but not non-membership proofs. And what we do is that we modify Merkle trees and by adding metadata inside leaf nodes, and this allows us to offer snark-friendly and efficient non-membership proofs. Now, we implement Verdict as a generic library for producing proofs of dictionary operations, and our implementation comprises approximately 10,000 lines of Rust code. To evaluate Verdict, we compare it against 3 baselines. First, a prior system called AAD. Second, a naive baseline based on Merkle-Patricia trees. And third, an optimized version of the naive baseline that is again based on Merkle-Patricia trees, but it's also batching updates. And we evaluate all of the systems on the quality of the proofs they create, the lookup proofs and the update proofs. So for lookup proofs, we look at the proof size and verification time. And proof generation time for lookup proofs is memory bound on all systems, so I'm not going to show you any results on that. And as for update proofs, we compare them on proof size, verification time, and proof generation time. So let's look at the lookup proofs. These are the proofs that, let me remind you, these are the proofs that the service needs to create whenever it responds to a lookup request. So for these, we see that Verdict actually, and let me say that the lookup proofs scale with the number of elements in the dictionary on all systems. So as we see, Verdict has the smallest lookup proofs. Proof verification time is fast, but it's not as fastest. It's around 5 milliseconds. And now let's look at the update proofs. So the update proofs on all systems scale with the size of the dictionary and the number of updates per epoch. Here I'm only going to show you our results as a function of the dictionary size, but in our paper we have more results for how all of the systems scale with the number of updates per epoch. So as you can see, Verdict's proof sizes are constant. They amount to 651 bytes. And as for verification time, Verdict's verification time is around 3 milliseconds per epoch, and that's faster than all of the other systems for large dictionary sizes, more than 65,000 labels. Now, as for the proof generation time, this is a little under 3 minutes. That's more than 3 orders of magnitude better than the AADs, but more than 4 orders of magnitude worse than the naive baselines. And that's actually the main limitation of Verdict, namely that producing snark proofs of updates still requires substantial CPU. And in the future, we could probably mitigate these costs by employing GPU or ASIC acceleration. To summarize, Verdict presents a new point in the design space for transparency dictionaries. It enables all users to verify that it is operating correctly. It does not require a trusted setup. It produces succinct proofs, and the overhead that it imposes to the service are affordable. Verdict's efficiency relies on 2 techniques that may be of independent interest. Sorry. So first, a zero-knowledge snark optimized for epoch-based services. And this snark-op provides amortized constant-size proofs and requires no trusted setup. And second, a snark-friendly accumulator that provides non-membership proofs. Thank you. And I'm happy to take any questions.